Yes, so video's going there. Let me pull today's lecture up. Today we're going to talk about engines and energy. Now, again, as we talked about last time, and so the midterm's coming up very soon. We've got, sorry, I didn't catch enable editing. There we go. Okay. So the midterm's coming up next week, a week from today, and I don't see that moving. And so Tuesday next week, we will review for the midterm. I don't have anything else new that I'm going to schedule there. I do not expect I'm going to have a guest speaker, that's the only day that they can come. That would be so basically on Tuesday, what we'll do is I'll review as long as you guys need me to and answer questions. And I don't expect that's going to take the entire time. So if you have one of the computer assignments that you're needing to finish up or work on, you'll get probably a substantial amount of time on Tuesday to work towards that. And the time will be yours to use as you need to. Okay, so we'll talk about the midterm, what it's going to look like, make sure we're comfortable with the topics, and then majority of the time you'll have to do what you need with it. Okay, so that's what Tuesday is going to look like, and that gives you guys kind of a catch-up day if you missed a lecture or you missed one of the work days and just fell behind on one of the assignments. That way you get access to that, and I'm available to help you answer any questions you need. So that'll be Tuesday, and then Thursday next week will be the midterm. Because I've got students that are in quarantine, I think I'm going to need to go with a digital version of the midterm. It's going to be online through Canvas, so we'll talk about all the details about that on Tuesday and make sure that's clear. Okay. So next Thursday you can come in here and take the midterm. If you want to take it from home, I would be okay with that. So either way works with me. Like I said, let me kind of make sure I iron out all the security issues and make sure I've got everything dealt with, and I'll talk more absolutes on Tuesday about exactly what it's going to look like. Okay. All right. Questions for me before we get started here? Okay. So let us then, the last topic that I put on the midterm, after the midterm there'll be a few other topics between now and the final projects we'll talk about as we're kind of working some guest speakers into the schedule. But this is the last topic that shows up on the midterm, and that's basically a simple study of thermodynamics. Okay. Now, thermodynamics is this study of energy, and we have devices that manipulate energy. But let's start with what is energy. Energy is simply a quantity. It's what we call a conserved quantity. It's kind of like mass or money, if you will. Money is kind of this conserved quantity. Unless you're a federal government, you don't just create new money, right? There's a finite amount of it. Same thing with mass. There's just this finite amount. Energy is the same thing. There's a finite amount of energy in the universe. And what is that energy? And the difference there is it's not like mass where you can feel it, or money where you can count it. It's a little different to kind of experience and measure. There are some ways to do that. What is it? Well, one of the best definitions I've seen for energy is, and this is kind of a paraphrase from a text we use here for Intro to Environmental Science. I was substituting for one of my colleagues one day, and the topic was energy, and the instructor knew this was probably a good fit for me and asked if I would mind talking to his class for a day or two, and no, it's fine. And this was the definition, kind of a paraphrase of the definition from that text, is it's a quantity that's and what does it do? Well, it influences the temperature, the motion, and or the state of matter. Okay, so it's pretty generic, but that's also fairly encompassing. It's this quantity, this amount, this thing that allows us to modify the behavior of mass, of material. Okay? Now there's two devices that we can point to, two generic categories of devices we can point to that affect energy, and that's engines and motors. Can anybody tell me, without looking ahead in the notes, can anybody tell me what is the difference between an engine and a motor? Does anybody know that?
Electric?
Electric is which one?
Motor?
Electric would be a type of motor, yes, and that's the most common type of motor that we see. It would be an electric motor. All right. Anybody else want to contribute? What's the difference between an engine and a motor, or maybe examples?
Is it one converts energy, the other uses it?
You're on the right track, actually. Yeah, it's how they interact with energy, and so they both convert energies. They both actually convert energies, and it's what types of energies they convert is the difference. So a motor is any device that's going to take. So a motor is a device that converts one type of mechanical energy into another. So again, the electric motor is the most common motor that we see, and it might seem kind of weird to think of electricity as energy, but electricity is flowing electrons, right? That's what electricity is moving electrons, or they're either flowing all in the same direction, or in the case of AC signals, they're moving back and forth in a concerted effort, right? So mechanical energy is when all of the objects, all the particles, the molecules, or in the case of electricity, electrons, are doing the same thing. They're moving in an orderly fashion. That's mechanical energy. So thermal energy is when you have kind of this chaotic energy, or the chaotic motion of the particles involved. An engine is a device that's going to take chaotic thermal energy and convert that into a mechanical form. Whereas a motor is going to take mechanical energy and convert it to some other type of mechanical energy. And the electric are the most common motors we see. Another type of motor might be some kind of a hydraulic or pneumatic motor, where you're using pressure or some kind of a flowing fluid to generate the mechanical energy. That's also a motor. Whereas an engine's going to have typically some kind of a heat source, right? So you're basically converting some kind of stored chemical or nuclear energy into heat, and then using that massive amount of heat to generate mechanical energy, motion, and get all of the particles or molecules moving in the same orderly fashion. Most of the time in rotation, just depends on what we're doing. So that's kind of the technical difference, okay? So within that, what do you think are, I'm gonna grab a red pen here. Let's see if this red pen's, that's not too bad, okay? So what do you think are some types of energy? Looking for the eraser. Well, that sucks. Pad came off the eraser. Need a new eraser. All right. What are some types of energy? What do you guys think? What are some ways we get energy?
Solar?
Solar. Yes. What else?
Motion, like with wind.
Yeah. Wind's a good one. I'm gonna put that one over here. What else?
Would water be hydro?
Yeah. Water or hydroelectric energy. Yeah. What else? Nuclear. Yeah, I'm gonna put that one over here. What others?
Gravity.
Gravity, yeah. So gravity generates, we can use gravity. Gravity itself is not an energy, it's a force, but what we can use it for is what's called potential. There's actually different kinds of potential, but that's gravitational potential energy. It will impart energy. Gravity will impart energy to an object. Yeah. What else?
Electricity, or like lightning.
Yeah. Yeah. I'm going to put electricity over here. So you have some potential for electrons to flow in an orderly fashion. And if you allow them to do that, that's transfer of energy. These are some good ones. Any others? Okay, it's a fine list to start with, right? Nothing wrong with that. There's two governing concepts. There's actually 4 laws of thermodynamics, but there's 2 main ones that we really focus on that really govern what we can and can't do with energy. Again, there's 4 laws. There's a 0 law, there's the first and second law you see here, and there is a 3rd law. But these are kind of the 2 that really govern what we can and can't do with engines and motors. The first law of thermodynamics, you've probably heard this one before, just not called the first law. That's the idea that energy cannot be created nor destroyed. It can only change forms. Conservation of energy. Again, energy is this quantity. There's only a finite amount of energy available in the entire universe. And we can't just create or destroy. All we can do is move it around from one form to another. The second law of thermodynamics, one of the better paraphrases I've seen for this is all processes result in an increase in total entropy, or any isolated system allowed to, over a period of time, is just going to spontaneously move to a higher state of entropy. Can anybody tell me what is entropy? Anybody talked about that in the chemistry class? What is entropy? It's okay. It's not a requirement for this class coming in. So that's not a prerequisite. Entropy refers to chaos, unpredictability. So entropy is actually how unpredictable is a molecule or a particle behaving. So the more unpredictable that molecule is, the higher the entropy is. Okay? So the air molecules moving around us right now are very high entropy, very chaotic. It's very difficult to predict exactly where this nitrogen molecule is right now and where it's going to be in the future. As opposed to the water molecules in my bottle here, okay? It's pretty easy to know that those water molecules are still going to be in here somewhere, right? They're moving because I've just stirred them up, but their motion's really constrained. That's very low entropy, and it's pretty cold. It's liquid, it's pretty cold. They're not moving around very chaotically. This is low entropy, where the air molecules will be high entropy. Right? And the second law talks about everything that you do, all processes that occur in the universe are always resulting in the universe being at a higher state of entropy. Okay? So the expansion of the universe itself, in theory, is irreversible. Once you've hit that point where there's now more entropy in the universe at this instant in time than there was the previous one, and there's no way to go back. Right? There's no way to go back to a state of lower entropy. You can cool something down, like this water has been cooled down, it's been refrigerated. So you can decrease the entropy of this water. To do that, you've got to generate more entropy somewhere else in the universe. The refrigerator generates more heat, puts more heat out in the air around the universe. Okay, so that's kind of the second law and what it does, right? And I've got this statement down here, kind of another way to interpret it is that all mechanical energy will eventually degrade to more chaotic thermal energy, eventually. Okay? All right. So, and before I move forward to engines there, and talk about some different types of engines, let's talk about what that means for our different types of energy here. So I put nuclear and solar together kind of in their own category here. These are types of heat. Right? These are types of heat. And actually both of these are nuclear energy. The sun is a large nuclear reactor that's emitting lots and lots of solar heat radiation or nuclear radiation because what it's doing is it's taking hydrogen and other smaller atoms and it's fusing those together into bigger atoms, and because there's so much gravity and so much mass, it's pushing those things together, and at the core you have this big nuclear fusion reaction occurring, and that generates all this heat, and that's just emitting all this heat out into the surrounding universe. and we're benefiting from that energy. And that's what drives all the processes here on Earth. Here on Earth, we use nuclear fission in nuclear reactors where we're taking a large uranium or plutonium atom and we're breaking that up into smaller pieces. And when we do, some of that mass gets converted to energy, right? And that emits heat. So, whereas the sun is basically doing a fusion, it's making bigger atoms. We're breaking down big atoms into smaller atoms here on Earth to generate energy. Okay, but both of which result in heat being emitted. So there's other types of heat. You can burning any kind of fuel source. You're releasing chemical energy as heat when you do that. So these are all heat types of energy. These are all, I've put these over here because I would suggest these are all mechanical types of energy. These are all mechanical types of energy. Now, the first law says energy cannot be created nor destroyed. It can only change forms. So the first law says there's no problem. Just draw one big arrow going back and forth here. First law says all of this energy can be converted back and forth and can be converted over here. And all this energy can be converted back over here. Back and forth. No problem. The example I always like to give is let's say I'm going to go camping, okay? Let's say I go to a big box store and I buy myself a nice electric heater. Right? You just plug in the wall and it takes electricity, right? Electricity, and it kicks out heat. Okay? It's real easy to do. Got all kinds of devices to do that. So I go to the store, buy a device that takes electricity, kicks out heat. But let's say I go camping and I need some way to charge my cell phone. All right? So can I take that electric heater, build me a nice big campfire, set that electric heater next to the campfire, and then hotwire the output plug on the electric plug on that heater, wire that up to my cell phone charger and plug my phone in? Is that going to work for me? No. But the first law says that's okay. First law says electricity, heat to electricity, no big deal. That's fine. Second law says no. This is chaotic entropy, high entropy energy. You can't just magically turn that into low entropy, very predictable energy. Right? The second law, it doesn't say you can't. It just says that there's a limit. The second law says that this is real easy. Going this way, going from low entropy to high entropy, that's easy. Very easy. You can do that all day long. The second law says that's basically what happens. The second law does allow us to go this way, but there's a limit. There's a limit. I can take heat and generate electricity or other mechanical energies from it. That's what an engine does. But there's a limit as to how much of this energy I can go this way. And the limit is that the total chaos in the universe has to be higher than I started. So these are low entropy, meaning there's not a lot of chaos. I'm making molecules move in a predictable fashion. That's fine as long as somewhere there's more molecules that are moving more chaotically than they started. And the total amount of entropy is more than what I started with. I know it's a little abstract, but that's the limit. That is the limit that we work within. The first law says go for it. Go back and forth. Second law says come this way, that's easy. Going that way, there's a limit. Just don't destroy entropy and we're fine. So how do we do that? Well, some technologies we've got a nice little GIF image from Wikipedia of a 4-stroke gasoline engine. So your engines that run on gasoline or compressed natural gas in your cars are going to look like this. You're going to have an engine in there, unless it's a rotary engine. That's another animal. But even then, it's going to go through something like this. If you're driving a little sedan, you probably have 4 cylinders in your sedan doing this, right? If you're driving a larger car or, you know, a kind of a performance vehicle, you might have 6 or even 8 cylinders doing this, but you probably have a number of cylinders going through this process. This is what we call the 4-stroke process. So you intake, then you compress, you hit it with a spark and it blows up, and then you shoot out the exhaust, and then you repeat, okay, over and over again. Wonderful process, pretty efficient. It only generates power 25% of the time right now, and it's done. And the rest of the time, it's relying on either the rotational inertia of whatever you have hooked up to this to continue the process, or in the case of most car engines, you've got 4 cylinders and you can stagger them to where at any point one of them's doing this, and then the next one's doing that, and the next one's doing that. So at any point, one cylinder is generating, it's not generating power, it's converting thermal to mechanical energy. And then it's relying on the other pistons to drive that process, get it through the rest of the process where it's not, that's on the power stroke. Right? So the goal is to have at least one cylinder on the power stroke at any time in a car, okay, or in a larger engine. If it's a lawnmower or something like that, I've got a 4-stroke weed eater, which I love because I don't have to put the oil in the gasoline, right? So if you run a 2-stroke engine like a chainsaw, you got to put the oil in the gasoline. That's a slightly different process. We could go look at a 2-stroke JIF and compare, but that's a lot more technical than we need to be here. With a 4-stroke, the oil's separate. It's down here. In a 2-stroke, you put the oil in the gasoline, okay, because there's nowhere for it to be stored. But anyway, I've got a 4-stroke weed eater that I love, but it's only got 1 cylinder, so you got to keep it at a very high RPM for it to continue the process. Otherwise, a blade of grass is going to stop the weed eater blades, and this process stops, and I got to restart. Okay. So if I run like a lawnmower or a smaller engine where there's only 1 cylinder or so, it has to run at a pretty high RPM, and it is pretty easy to stop it, because if you catch it in between strokes, if you catch it anywhere other than stroke 3 here, the process stops. Okay, but that's what we call a 4-stroke spark ignition sequence. Diesel's a little different, but let's not get into a lot of technicality there. Most engines you would encounter, internal combustion engines, look something like this. Okay, so that's a good way to convert thermal energy, right? So I'm converting thermal energy into nice, orderly, spinning mechanical motion, and then I can hook this up to wheels, or I can hook it up to spinning blades on a lawnmower. I can turn that rotational mechanical energy into other types of mechanical energy. Okay, but I've got to convert some of this to that to do that. Now, if we look at something like a coal-fired power plant, right? I'd like to draw on this, so I'm going to put this. Okay, it's still reasonably in focus. I'd like to be able to draw on this. So if we look at this coal-fired power plant, okay, nice diagram of that. You got a coal source over here. Okay, so I've just borrowed a diagram off the internet here. You got a coal source, a fuel source over here. We powder this up into a fine grain where it's easy to burn. We put it in some kind of a burner, and basically what you're doing is you're putting in a lot of heat right there. So in most thermodynamics courses or thermal science courses, we use Q for heat. All right, so we're putting a lot of heat in right there at some point. Now what we do with that heat is we use that heat then to boil off water. It's a steam engine essentially. We're generating steam. So we generate steam, we get that steam to come out at a very high pressure, very high temperature. We run that steam then into what we call a turbine or a turbine. Right? And the way the turbine works is it's kind of like wind turbines, or one example most of us can kind of think of, right? This is not unlike that. It's different, yes, but it's similar. The steam turbine in here, what we do is we inject this high pressure steam into this device that's got these fan blades inside. These little thin metal fan blades. They're made of aluminum or something like that. What happens if I take a fan and I go outside on a windy day? It starts spinning, right? And you can actually, and I don't do this and say, Professor Fowler said to do this, you can actually use that fan to generate electricity. If you spin it fast enough, you will actually get electricity coming out the other side, okay? Again, don't do that. I'm not telling you to do that. But the turbine here works much the same ways. You inject into this device with these metal fan blades inside, this high pressure steam moving really, really fast, it's gonna make the blades inside spin. All right, so you get these blades inside start spinning, and as that steam is allowed to slow down and expand, you're basically extracting as much energy from this high pressure, high temperature steam that's absorbed all this energy from the heat source. You're using that to cause really large fan blades to spin, and you use those spinning fan blades then to turn an electric generator, and so then you're putting out mechanical energy. We call that electrical work. So you're putting out a little bit, and actually probably a good amount. So you see I've got power lines here on this diagram. You're kicking out electrical work to put it into the grid, and then to be transmitted to other places.
Professor Paul,
Yes?
those blades, do they spin just out of the sheer chaos of the molecules, or is it that the steam is being blown in there much like the wind is blowing outdoor?
Both. Both. The steam molecules are somewhat chaotically. We try to direct them and get them to move as much as we can into the right direction. But then once they get inside there, then they're pretty chaotic. But we try to build those fan blades in such a way, and they're in stages to where they're directed from one set of fan blades to the next set of fan blades to the next set of fan blades, and all those blades are tied to the same shaft. So we try to limit the chaos as much as possible, but it is high energy, very chaotic flow. But we try to get it just as orderly, so we get as much orderly out of it as we can. Yeah.
So are those fans like linked to gears or belts that go to the generator?
Absolutely. Yeah, we've got to get these spinning at one speed or consistent speed to get electricity at 60 hertz or 50 hertz, wherever we're at in the world, whatever the grid uses. We've got to have magnets rotating in a coil at that speed. So using gears or pulleys, we can adjust what output we get out of the turbine and get to the generator at the right speed. Yeah, there's going to be some kind of transmission device between the two, I would imagine. Or we've got to be very careful about controlling that turbine to where it spins at the very specific speed we need it to. One of the two. Which one's easier? Probably easier to control the steam flow in and get the turbine to spin at the right speed. That's probably easier because that's one less device to fail. Yeah. Other questions? These are good ones. They're all good, but definitely good questions. Okay. So we generate lots of heat in, some electricity out. Again, remember the second law says you can't take all of this and go this way. Right? There's got to be more chaos somewhere in the system. Well, so what we're saying, and again, the first law says all this energy has to be conserved. Look, I've got this huge arrow here, and I've got a smaller arrow here. That means not all the arrows accounted for, right? There's got to be, I've got to reject, so this is a cooling system down here to where I'm losing heat here. I've got some kind of a vapor column here. I'm going to kick out some heat there. All of this heat in has to go somewhere. Because if it doesn't, this thing blows up eventually. You keep storing energy, more and more energy in, more and more energy in, and it has to be conserved. So it doesn't go somewhere, this thing blows up. We don't want it to blow up, obviously. And I can't get all of this energy out here. That's the second law. So it's got to go somewhere. So we find various places to dump it. River, stream nearby, out into the atmosphere. And that we use that then, that repeats the process. So the steam that runs through the turbine has to be cooled down so it can go back into the furnace. So I got to cool the steam down, get it back to water, and then get it back to where I can inject that water back into the furnace at a high pressure. So I'm going to have various systems throughout that does that. Okay. Now, the reason I wanted to draw on the board is because then if we look at a nuclear power plant, notice almost had that perfect. I need to adjust the size and layout of this picture so it matches up a little better. But you can see I don't have to move these much at all. Right? Massive heat source, that's my nuclear reaction, trapped inside some kind of concrete tomb, so if something goes wrong, hopefully most of it's contained. The Russians figured that one out, right? Don't make sure it's trapped in somewhere. Notice I've got heat out going through a steam column here. I've got heat out going through a cooling lake down here. I've got, again, it's essentially the same diagram. I've got some electricity going out as a result of boiled off steam running through a turbine, turning a generator, generating electricity, and that goes out to the grid. Yes?
You're talking about Chernobyl, right?
Chernobyl is an example of where they didn't have a really good containment system on the nuclear reaction, and they just kind of willy-nilly were experimenting with the reaction one day, and just to see what they could do, and it got away from them, and they didn't have good safety protocols in place, and when it blew up, there wasn't anything to contain it.
And that was gonna be my question, what makes them so volatile? Because you hear about them being very volatile, and they try not to have a lot of population around
Neglect.
these.
The reason they're volatile is neglect. If we don't neglect them, they're good. The biggest challenge is what do we do with the radioactive waste? And that is a challenge, and I think we've got some pretty good systems in place. In Japan we had that issue where we put one right beside the ocean, right? And then when the tsunami came in, and there was some neglect in place, where there were recovery protocols in place, but they had been neglected. So there was actually a way that could have shut itself down, but it had not been maintained properly, from what I understand, and so it just got away from them. After the worst case scenario, the recovery from the worst case scenario didn't work because it had been neglected. Chernobyl had just completely neglected any safety. Right? Here, it's very rare that we have any issue here. It's not to say we're perfect, but again, it can be controlled.
So here, who is the governing entity that makes sure that these facilities
Sure.
fall?
Yeah, who would be the governing entity to make sure it doesn't work? And I don't know the best answer to that question.
Is it just the EPA, maybe?
There is an entity. There is a government entity, and I don't think I think EPA has some role. It's not EPA. It escapes my mind immediately, so I don't want to make something up.
Sure.
But yeah, there is a governing entity here, and I'm not going to speak to how good it does, but yeah. Alright. But again, notice the similarity. Still an engine. Heat in, some power out, remaining heat's got to be rejected. And the same thing with if we look at the 4-stroke engine, same thing. Energy in, some of it gets converted to mechanical energy, remaining energy has to be rejected out. It's got to go somewhere. We don't want this thing to blow up. And then you've got a radiator system keeping all the components of the engine cool, because the components of the engine are going to absorb heat as well. You've got to keep them cool. All right? So the same basic process. It's an engine. Okay? Now, hopefully that helps. Well, what I like to do is I like to talk about another concept called a Stirling engine. Right? And one of the reasons I like to talk about a Stirling engine, one, is because you've probably never seen it. Two, because it's actually pretty easy to construct one. And three, I think it's just underutilized. The idea of a Stirling engine, where we saw earlier, you got to have heat in, and then you got to reject the heat that you couldn't convert to work. One thing that the Stirling engine does is it takes a gas and it passes that gas back and forth between the hot side and the cold side. Okay? So you heat up the gas in one end of the chamber, and then you cool it down on the other. And when you do that, something really interesting happens. So if we look at, again, another reason I like to talk about this is because it's not too terribly complicated. So those of you that are watching this those of us joining us from the internet, watching this on YouTube, you get to watch a YouTube video of a YouTube video. That's kind of fun. Hopefully this comes through. No, thanks, go away. I'm gonna turn this down just a bit. All right, so these links are available to my students here. So this guy's just put a fuel source. He's basically building a little tiki torch. Right, so he's just put kerosene or something like that, maybe some alcohol into a jug there. He's gonna put a wick in there. And we'll talk about his setup here in a second. It's not the best video, especially when you blow it up. Sorry, but I think we kind of get the idea here. All right, come on, buddy. Get it going. All right, so he's going to try to light it. It's a little slow, so I try to provide commentary. Who can tell me he's made a mistake here? Anybody know what this is? Anybody put together a tiki torch for the first time?
He did wet the fabric.
He didn't soak the wick. So notice he's trying to figure, why is it burning? He doesn't know, right? Yeah, he didn't wet the wick to begin with. He didn't let the wick soak long enough. Now it's soaked in enough, so now he's going to get it. So he's got a fuel source. You got chemical energy, he's burning it, he's releasing thermal energy. Okay, let's do something useful with that. So he's going to take that heat source then and show it to us, I guess. I don't know. Yeah, he's going to show it to us. He's going to check his setup here. So he's got a test tube with marbles in it. That's easy. Test tube with marbles in it. And a rubber stopper with a hole in it to where air can come out of this test tube, go into this. He's got a tube here connected to a syringe. That's pretty easy, right? Nothing too complicated. Notice what happens as the gas heats up on this end. What happens when I heat up a gas? What's the gas do? It expands. Okay? So it's expanding.
It's causing the syringe to expand.
Yes, so the air is moving from here. As it expands, it's pushing into this end, into the syringe, and the syringe is pushing up as more and more air gets pushed into the syringe. Now watch what happens when the marbles start rolling. It's kind of like the roller coaster at the big first hill, right? Here it goes. What? It's witchcraft. What's it doing? That's pretty cool. So we think about what's going on there. As those marbles slam down into this end, that pushes all the air out of the hot end. Forces all the air out of the hot end. Where does it go? It comes down here to the syringe end. What happens when the gas cools off? It contracts. So you push all this hot air out of this end into the cool cylinder, and it wants to contract. And a Stirling engine is an engine where you use the expansion in the hot side and the contraction in the cool side to push and pull the drive mechanism back and forth, back and forth. So you're getting power on both ends, right? Or you're extracting, I should say, power from both ends. That's pretty cool. I like showing this because you can look at that as like, what? We could do that, right? That's not hard at all. And I've got some other examples in here. Here's one where, if memory serves, I think this video is even worse, sorry. So he's got a big heat source. Same type of setup. He's got a test tube with marbles in it. He's put black, or this individual, I don't know if it's a he or she, we don't know. They put black on this end of the test tube to absorb more of that heat, okay? And they put the syringe, or the cold cylinder, if you will, they put it underneath, so it actually lifts directly. It's a little more efficient. Not greatly efficient, but you get a little better feeling for it, and you see the marbles are just now starting to move. Same phenomenon, right? A little more efficient.
So what is this used on today? Like, I imagine that it's used for much larger things.
No.
So it's not?
No. We've tried, and that's where we're headed next, right? Yes,
Do we
yes.
know kind of what's keeping them from using it efficiently? Is it just?
Do you want the political answer, or
of
the
course,
political
that's what
answer
we
is, from my observation, you've got large petroleum companies that
Gotcha.
buy politicians that can influence.
The funding
Yes.
for more research on this, okay.
Yes.
That's
Or
unfortunate.
that can affect the price point of other energy sources. Yeah.
Where would the point of the most energy, mechanical energy, be
taken? Is it the pivot point? Or could you put like a piston in the syringe that rotates?
I love all these questions, and that's how can we make this better? Is basically is that what I'm hearing you're saying?
How do you output it to electricity? Because like the generator has to turn somehow.
Boom, perfect, exactly. So let's look at this one. I think this is going to answer your questions. Okay, I love this question. Let's see if we can get you an answer. And this one's on a sorry for the advertisement. People got to make money. Right? And hey, you're putting together good quality ads or good quality videos.
We get a lot of questions about this Stirling engine regarding the power that it has. This engine in the previous video,
This is a better version.
Parabolic mirror, basically just a shading mirror to power.
And he's going to go around it. I'm going to talk about kind of how this one works.
That small of a mirror could power that engine. That didn't really go that fast or have that much power in that video. So what I'm going to be doing in this video is taking a large Fresnel lens on a stick, and concentrating the sunlight like this.
Okay. So you're asking about how can we make this better, right? How can we hook a generator up to this? So this is a different layout, but it's the same basic idea. This is the hot cylinder. I know this is not the best freeze of it, but this is the hot cylinder where he's going to shine the sunlight right there on this point where he's going to generate heat, and the gas gets passed back and forth. This is the cold cylinder where the gas cools down and contracts. And so it's using the contraction of the cool cylinder and the expansion of the hot cylinder back and forth to cause this wheel to spin.
Let's see if we can get it just right.
He does put his camera on a monopod, so if you get motion sickness, just give it just a second here.
Sweet spot. Now, what I've done is the black paint pretty much got burned off from previous tests. I put a small piece of that stainless steel wool in there. So we're going to see how much power we can generate. I'm going to be hand holding this, so I might be wobbling around a little bit. So it's not going to be perfect. All right, so here we go. I don't want to catch the wood on fire. I'm going to try to focus it right on that stainless steel wool.
So he's put stainless steel wool to absorb most of the sunlight and trap it instead of just passing it through the air in the cylinder. Now see how it looks to us like it keeps changing direction? That tells us the speed. So about 3,600 RPMs right now, that where it switches, that will occur at 60 frames per second. That's about 3,600 RPMs is where that occurs. You can see it's getting it. It is flat getting it.
Put some resistance on it.
So if I was to put an electric generator on this, that's basically what he's doing. You put some resistance on this side. So we could put an alternator out of a car on this and generate 12 volts real easy. I don't know if this one's big enough to really handle a decent sized alternator or not. I'm not the person to answer that question, but that's the basic idea. You hook up some kind of generator to this device and you generate electricity.
So theoretically, if like the power grid just went out, right, and I have a water well, if I got really good at this, I could power my water well.
Yes.
And I'm just going to let it run down.
You see, he's taking the heat off it now. And it's because there's so much heat still stored in that steel wool, it's still going to go. And now you can actually see the whole thing. You can see where the hot cylinder, cold cylinder, okay? So that's kind of cool. Now, the question, earlier was asked about, I can't use names because we're going on the internet, right? But the question earlier was asked, well, what's preventing us from doing this? There was actually, I found this video, there was actually a company that, I believe this company no longer exists, okay? We're going to turn them down. They've got cool advertisement music in here, and I can turn it back up here in a second. We'll turn it down for a moment. So this was a company that actually tried to make these on a commercial level. Right? Remember the satellite dishes maybe your grandparents had, the big ones out in the backyard, and had to move to track, to point to this satellite and then it points to that satellite, right? Same basic idea. The difference is this one's tracking the sun. So big mirror where the guy in the last video, he had a big, like kid with a magnifying glass burning the ants, had, a big lens to focus the sun's rays on one point. Here they're using a big mirror to collect all the sun and set the focal point out here where you've got a Stirling engine out here at the tip where the receiver and the satellite dish would be. Here it's an engine out there. And so there's a little set of cylinders out here in this end that's in the Stirling engine generating the power, and these things just track the sun throughout the day.
It's kind of like solar energy, you know what?
Yeah, it's just a different way of utilizing the solar heat to generate electricity. Right now, one of the things I like to point to here, again, this is an advertising video, right? But there's some really important one to talk about in here. So they're talking about the advantages. As opposed to wind turbines, it doesn't have to have unobstructed, nothing can be built around a wind turbine because you need the most wind you can get out of it. These could just be sitting out. As you see, they just put them out in the yard, right? You can scale these up is what they're saying. You can put a whole bunch of them out on a hillside or just one or two. So, there's some advantages, some disadvantages. Obviously, the sun has to be shining, but when it's shining, it's be nice to just get something out of it. Right? Another thing.
That's the problem right there.
Yes, transmission. That's exactly right. One of the big challenges with solar energy, or as we know in our state with wind energy, that energy is available in places where people are not. How do you get it out, right? And so one of the challenges of building the big wind farms is how do you get that energy from that location, the remote location, to where the people are actually going to consume that energy. You have to build transmission lines for those types of structures. These, if you're going to put them in modular in one specific location, then it can be used at that location, right? And that's one thing we do have to kind of look at. Wind turbines, the bigger the wind turbine gets, so if you double the size of a wind turbine, you quadruple the amount of energy available because it's based on the area, right? And therefore, if you double the diameter of the circle, you just quadruple the area of the circle. So there's 4 times more. So as you increase the size of the wind turbine, you increase the amount of energy available. That's what we've done with wind turbines. We tried to build them progressively bigger, and that's what makes sense. Not the case here. Right? So just kind of a different take on it. From what I understand, this company went belly up in the last recession because the energy prices went nuts. It completely destroyed their price point. We're at a point now, at this point in history, where this is probably a possibility. But yes, the transmission lines is a big issue. That's not necessarily an issue here. You do have to maintain your own units. It is what it is. There's one more thing here that I like to talk about. All right, so they're talking about the efficiency. They're saying, look, we can use regular manufacturing to do this. That one. 24% efficiency. Now, to get to where we really understand what that means, we got to get through a little bit of math to get there, and that's okay. The efficiency of any engine is going to be basically, well, a lot of times we like to say it's output over input. That's efficiency. So a lot of times we'll use this Greek letter eta to represent efficiency. Okay, efficiency is output over input. In the case of an engine like this or a device that generates electricity, that's going to be your electrical work, W sub E, your electrical work out. That's your output, divided by the heat from the sun going in. Okay? Now, something you need to understand when we're talking about electricity. Electricity is measured in a quantity we call voltage. Okay? And voltage is basically how hard, what is the pressure? How hard are the electrons being driven to move from one location to another? That's basically what voltage is. Okay? If I plug into the wall down here if I plug into the wall down here, my voltage looks like this. It starts out up here at like 120. Not exactly. Those of you on the internet, don't blast me on this. I know that's the root mean squared value. That's not germane to our discussion here. You start out here at 120, and then it goes down to minus 120. And it goes back up. And it repeats. Up, down, up, down. And if you want to learn more about this, learn about the voltage wars, or the war of the currents between Edison and Tesla. It's an interesting thing. Let me put it this way. If I need rotational motion, it's a lot easier to turn this into this, okay, than it is to turn this into this. Does it make sense? If this is what the electrons are doing, is the electrons are moving back and forth, it's real easy to turn that into rotational motion. If that's what I need, that's real easy to do. Okay. Now, if I look at a battery is going to be typically anywhere from 1.5 volts for your AA's and your AAA's and your D's. Those are all single cell batteries at 1.5 volts, way down here. Maybe your car battery's up at 12 volts, somewhere down here. And they do this. That's DC. The electrons are not going back and forth, they're going in a straight line. Okay, that's DC. So, you see the difference here. You know what a solar panel does? This one. Solar panel generates DC at low voltage. If I need high voltage, I got to stack a whole bunch of solar panels together. You know what the efficiency of a solar panel is?
10%.
It's not good. 10% might be a little low, honestly, but it's not high. It's not 24%. Now, here's what you also have to understand. That is, for a solar panel, right, it's going to be maybe, I don't know, I really don't know what a modern one, but I think 12% is not terrible. Okay? Not huge. Let's say that we get one of the really high efficiency solar panels they put on one of the Mars rovers. I think they might have been able to push somewhere in the 30%. So let's say, absolute theoretical best might be 30%. And that's probably way too generous. Okay? But understand that's down here. Right? That's down here. If I want to push it back in the grid, I need an inverter. That might be 50%. Converting from this battery power into grid power, maybe 50%. Maybe 50%. So of the 30% of the sun's energy I'm converting from a solar panel, only 50% of that's going to get back in the grid. We're talking about 15% for the best possible solar panel and a really good inverter. I'm talking maybe 15% I can push into the grid. Now, if I'm using my solar panel to power devices that just need battery DC input, that's fine. You do have to understand how electricity works, and to most people that's magic, so they don't get any of this. Okay? So explain to somebody, don't turn your solar panel into electricity that you plug into the wall and then use that and convert that back down with a DC adapter to power your phone. You're just generating heat the whole way. Okay? That's the second law of thermodynamics working for you. But you do have to understand what electricity is and how it works to even have a chance at knowing that's a bad thing to do. Okay? Using a solar panel to generate wall electricity so I can plug my refrigerator into it, it's possible. I don't know it's the best thing to do because it's just not efficient. Again, at best, crazy efficiency, maybe 15%. They're saying because they've got rotational device spinning. So they can generate AC electricity. They don't have to generate DC and then convert that DC to AC. They are generating AC. This is actual 24%. They're saying they can get about 24% of the heat from the sun and turn it into electricity, instead of maybe getting 30% and then losing half of that to get it up to wall electricity. Does that make sense?
And it all boils down to the way that the molecules are moving, is that correct?
That's a big part of it. You know, to generate electricity, you've got to have magnets moving through a coil of wire. So you're basically pushing the electrons within that coil of wire in a certain direction. Or in the case of AC, you're pushing them back and forth because the magnets are moving them one way, and then the south pole comes around that pulls the electrons the other way, right? So but as opposed to a solar panel where it's just pushing electrons one way consistently, because you got light coming in and they're set up to where they just push electrons in one direction. So they're producing DC. Does that make sense? Kind of? No? Okay.
No, it does.
It does come down to the motion of the electrons. Yes. Yeah. Question.
So the Stirling engine changes the solar directly into AC, right? So the Stirling engine has a rotating shaft, and I can hook that rotating shaft up to a generator that generates directly AC. So rotating shaft, like you said, is that more efficient than like a voltaic cell in a solar panel?
It depends on what kind of electricity do you need. Do I need electricity to charge a battery?
Yeah.
Or do I need wall electricity so I can maybe run a refrigerator or a vacuum cleaner, something that has a rotation inside it?
Is the majority turned into wall and then down into for batteries?
Well, I mean, that's what we're doing now. Because we haven't really, we've always had this abundance of energy that's cheap. So it doesn't really matter how efficient we are with it. So we've just built whatever works. And it's cheap to work. Sorry, that's what you guys get to come into. But if you don't understand what the problem is, you can't solve it.
Yeah, it's interesting.
These are good questions. I'm glad you guys are engaged. What else, guys?
So wind energy, which one does that turn? What does that turn into?
It's the same basic idea is because that's a rotation, right? You got a big rotating shaft. You can turn that directly into AC energy. Now, I mean, your alternator in your car, that's taking rotation, and it's converting that into DC energy. So depending on what's going on with the magnets inside that generator, you can convert either one. But it's it's real easy if I've got rotational energy to make AC electricity. That's real easy. You actually have to intentionally turn that rotational into DC energy. Your alternator has special circuitry inside it to force it to come out DC.
So is the inverter for the solar panel that's only 50%? Is it using that other 50% to try and make that into the AC? Is that
What
or is it just excess that it can't?
It's just generating heat.
Heat.
Because what happens, what that inverter is having to do is it has some way that it probably mechanically, I have not looked inside a lot of inverters, but most likely it has some way that either mechanically it switches the flow one way and then switches the flow this way back and forth, or it's got various circuits inside. And every one of those circuits is less than 100% efficient. And you've got chains of them. And so what they have to do is they have to switch the direction of the electrons back and forth constantly, and you've got to amplify the signal. So there's going to be, the process of switching it back and forth is less than 100% efficient. And the process of amplifying it up to wall voltage is less than 100% efficient. And so you stack all of these efficiencies, every point in the process you're losing energy. Now again, and where does it go? Heat. Those things are hot. Just like your cell phone charger. Your cell phone charger is stepping this down, right? And then it's turning it from back and forth to straight. And all those processes are less than 100% efficient. So those things get hot because where does that energy go? It's just heat. And then your phone's not 100% efficient, so your phone's hot, so your phone's emitting heat as it's charging because it's good. That efficiency is actually fairly high, but it's not, again, 100%. So again, if I've got solar voltaic cells and I want to charge batteries with them, that's fine. That's okay. If I actually want to run my refrigerator on it, because that refrigerator has a motor inside running the compressor, that needs this. Or something that converts that for me. Again, if the energy is cheap and readily available and with no consequences, then we don't have to be real concerned about efficiency. I think we're at a different point in our lives now, though.
So basically the Stirling engine is just a better way to conserve that energy that you're getting from a normal solar panel.
It's a tool. It's a tool. I'm not trying to sell this as the end-all be-all solution to all of our problems. The end-all be-all solution to all of our problems is understanding of this versus this and the efficiencies associated with them. And this provides one possible solution. If I need wall electricity, this is a better way to do it than solar voltaic cells, in my opinion. And I think it's easy to show that mathematically. Yeah, again, don't get me wrong. I'm not saying the Stirling engine is the end-all be-all. It's a tool we need in our toolkit. Because I mean, you're basically taking solar energy and you're making wall electricity out of it. Now, it's having a device that's going to track the sun exactly and get the focal point on all that solar energy right at the sweet spot on that engine. That's not trivial. That's not easy. It's doable with the technology we have today. Now, can I do it to where it does it right every single time? Well, it's doable. It's not easy, and we're better at it now than we would have been at any other point in our history.
And in the grand scheme, we kind of need versatility, don't you think? Because
yes.
With it seems like every time we have a change in administration, we're all about oil and gas, and then we're all about wind energy, and then we're back to oil and gas. And I mean, it'd be great if there was just one more factor that could be tapped into without ticking off both sides, because that's what it comes down to.
Yes, if it is impossible to manipulate the market because there's too many variables to manipulate, then yes. That's the best case scenario.
For the consumer.
For the consumer, yes. Yeah, not the best case scenario for a particular entity that's only focusing on one variable. Yes. For the consumer that just needs it to work. Yeah.
So what kind of energy would like a fusion reaction be? Because you're saying that fission would be more of an AC because you're converting it. What would fusion be?
Well, that would be... That's what this is. That's a fusion reaction right here. So all that's going to do is generate heat. What do you do with that heat?
Right. I thought that was that not fission?
I see what you're saying. So fusion's but the fusion's going to be the same way. The fusion's just going to generate heat.
Gotcha.
Yeah. So in either case, that's just your heat source. Whether it's fusion or whether we can solve fusion. Potential energy output, the heat available out of fusion is much higher than what we're getting out of fission. So that's kind of why it's broadcast as this holy grail is if I can take hydrogen and smash them together and generate helium, the energy released from that process is much higher than, at least that's my understanding. So it's going to be much higher than, and potentially if we can figure out how to control it, there's more potential there. There is, and to not get into a lot of the technicalities, there's one of the limits associated with this idea of efficiency that comes out of the second law of thermodynamics is that the higher the temperature difference, so if my heat source is the higher the temperature of my heat source and the lower the temperature of where I'm rejecting the remaining heat to, the bigger the temperature difference between those 2 points, the higher theoretical limit I can have on my efficiency. So if the fusion reaction can occur at a much higher, and I don't know this, that's one of the things that comes to mind, is if that fusion reaction, if I can maintain that at a higher temperature than I can a fission reaction, then my potential efficiency goes up as well. And that's true of any process. We looked at for a while of incorporating ceramics into engines, into metallic engines, to try to increase their ability to operate at a higher temperature, thereby increasing the potential efficiency that engine could operate at. If you could prevent the gasoline or whatever your fuel source is from blowing itself up. Right? That is a limit. Yeah.
So like the heat lost in the cooling, like you were pointing out, and basically, is it worth trying to raise the efficiency by targeting spots, like targeting everywhere you can see where heat and energy is being lost? Or is the process of diffusion into steam, is that like is that what they focus on, or is there engineering specialties in like focusing on the heat and
Sure.
energy loss to raise efficiency, or like?
So if I understand your question correctly, and I'm also repeating for the video also, right? You're asking about, does it make more sense to try to track down more of the heat and try to minimize the losses? Or does it make sense to maybe have a process that's more efficient on the front end? Is that kind of your question?
Yeah, I was just thinking about how you pointed out how there's energy lost. You
Mhm.
pointed out underneath the where it's being transferred to the fans, or
Mhm.
the turbines, how it's lost in that process because it's being cooled on the pathway there.
Mhm.
You say insulate?
Yeah, insulation.
Mhm.
Yeah, but
Yeah.
that's one solution. I was just wondering, is there an actual field of like focusing on where is it worth focusing on where it would be lost in that example of being traveling to the fans, or is it just not
Sure.
that much lost there?
It's both. It's definitely both. I think that's definitely, we want to look at how much is too much to be rejecting, right? How much are we sure we're getting as much of this as possible, right? And you know, is there any way we can capture some of this and kick more of it out? Yes, all those are things that we can, and most institutions, you know, if I'm operating a power plant, it's in my interest to do exactly what you're saying, to try to say, can I minimize the amount that I'm actually rejecting to the environment and kick out as much of that energy as electricity as I can? Yes, that is in my interest, and I think a lot of entities do that. There's a limit, and so they do hit a point as to they can't really increase the efficiency anymore. I think it's both. I really do think it's both. I'm not saying that we should, in my opinion, we should continue with the electricity sources we still have. I think we just add more versatility. We consider other sources, and we consider what type of electricity is most efficient to produce from this type of device, and am I using that electricity in the most efficient manner? To your effect of, as I mentioned, if I'm using a solar panel to power my refrigerator, there's all kinds of places I'm losing heat to do that. Exactly what you're talking about. Can I minimize that heat at various places? Are these institutions doing that, the ones that operate the power plants? I think they should be. It's definitely in their interest to. I'm not going to say they are, but I think they should be.
I was just curious. I was wondering like how, if these systems are almost perfect to where they don't focus on it because they're getting the maximum percentage they think they can get out of it, or if we're at a stage to where there's a lot of improvement in these systems that are worth going into a career focusing on.
I think they're pretty good, honestly. I really do
Yeah.
think they're pretty good.
And there are professional engineers out there, and I can tell you from what they make like $60,000-$70,000 starting off. And for example, in oil and gas, their direct focus is to make sure that there's no energy loss, like between compressors, because it has to be at a certain temperature, and the molecules have to be moving in a certain fashion in order to make it down the line, right? Because they go for refinery like hundreds of miles from here. So their direct focus is to make sure that that fuel is moving and fast enough, the movement of the molecules is fast enough, the heat is just right, and that's their entire focus. And starting off, that's what they're making. Mechanical engineers.
Yeah, I'm not going to say there's not additional potential, but I really think that there's a lot of effort on that.
Yeah.
Other questions? We've only got about 5 minutes or so here anyway, so. All right, guys, I'm going to turn you loose. Thank you for your time.
Thank
This
you,
one-
that was really, really good.